Okay. Oh, sorry, 1 second. Okay, let's get started. So welcome back to CS479, Machine Learning for 3D Data. Before we get started, a couple of the announcement. So I guess everyone submitted the solution of the assignment one. So how was the assignment one? Do you have any comments and feedback for the assignment one? Was it okay? Was it too easy, too difficult? Any comments for the assignment one? Yeah, so now you won't be able to send a message to the everyone, so please send the message to me. Do you have any comments for the assignment one? Any comments? Okay. Was it too easy or too difficult? Any issues with the K-Cloud? Yeah, so obviously the assignment one should be the easiest the assignment, but there might be some kind of some technical issues instead of like in terms of like installing some libraries and basically handling some things in the K-Cloud. So also for the assignment 2 and 3, you would need to basically install some libraries or something. So please start the other assignments as early as possible. And also it's now also time to start the assignment 2. So the assignment 2 will be about the neural rendering that we are going to discuss in the couple of the weeks, this week and the next week. So please start that for now and see how it goes. And one the announcement is that we are going to have a guest lecture. So we are basically supposed to be two guest lectures, one before the midterm and one after the midterm. So right before the midterm week, obviously we don't have the midterm, but before the midterm week, we're gonna have a guest lecture by Niloy Mitra, who is a professor at the University College London. So he's visiting KAIST, so there will be also the great chance that you can also have some kind of the chance to see him in person. And the thing is that he won't be able to give the lecture in our regular slot. So the plan for now is that we are going to have the guest lecture on the October 10th, which will be Tuesday, 4 p.m. So I'm going to make this as kind of some hybrid the lecture so that the online people can also join. But for the people basically staying in this campus, please join this lecture offline. So I'm also going to announce the location soon. So that's kind of one thing. And also, if you check all the schedule, basically also we have the deadline for the project proposal. So please also check out all the schedule for the project as well. So the plan for now is that you need to basically submit the project proposal for each team. And after that, there will be some kind of the mock-up kind of the process. So you also need to submit the results of the mock-up of the project. And also after that, you need to also need to do some kind of the project pitch, which will be some kind of the very short the video presentation. So the deadline for the proposal is this coming Sunday, September 21st. And the thing is that you will need to basically submit a write-up with all the information for the project. And also the idea is that you will just need to edit your submission in the open review. So if you now go back to the open review for each of the team, you will be able to see the kind of the item for the proposal. So you'll need to basically edit your submission by just adding the write-up for the project proposal. So all the details are also explained in the course web page. So please check out all the details. So yeah, all the details basically there. Any questions for the project proposal? If you also have any questions for the project proposal, I also recommend you to come to the office hour. So we're gonna also have the office hour tonight at the 7 p.m. in the N1 building. So please join us, and also you can ask some questions to me or our TAs in Slack. And also we slightly change the policy for the quizzes. So basically the thing is that you will be able to also check out the participation discourse that our TA is basically grading. So our TA basically shared the link of the participation discourse. So please check it out. And if you have any questions for that, please also send a message to me or the TA in Slack. And also from today, you won't be able to send a message to the public. So please send a message to me in the Zoom for all the quizzes. Any questions on this? Yeah, so far, basically, we discussed some kind of the neural net architectures that can process the point cloud as the input. So one question, is there any other office hours in this week? Well, I mean, we are not planning to have some other the office hours this week, but if you cannot join the office hour today, feel free to send a message to me or the TAs, then we will be able to basically schedule some time for the chat for the office hours. Okay. Any other questions for the office hours or some other things? Okay. Moving on. So far, basically, we discussed some kind of the neural net architectures that can process the point cloud data, especially as the input. So we are basically making some kind of encoder. And last time we also briefly discussed some ideas, then how we can also make the decoder with some kind of the loss functions for the reconstruction, right? So actually, we skipped some of these slides in the previous lectures, but actually there are some kind of the 3 different ideas in terms of defining some loss function for the reconstruction. Have you checked the slides in the previous lectures? What are the 3 loss functions in the slides? This is the first question. Yeah, so I recommend you to basically check out the slides in the previous lecture that basically include all the information about the loss functions that we skipped a little bit. Basically, also the yeah, I was asking the loss function for the decoder, not the decoding architecture. Yeah, so please check out. So the assignment 1 was about implementing the autoencoder with the chamfer distance, but you could also use the Earthmost distance as the loss function. And also, it's not that good idea to use the Hausdorff distance because it's very slow if you use that for the training the neural net. But basically, yeah, that can be used for some kind of evaluation of the reconstruction, the quality. So we discussed basically the 3 ideas for the loss functions. So please check them out in the lecture slides in the previous lecture. So those are basically very simple the idea. Basically, if we make some kind of the autoencoder that can basically compress some kind of a set of the 3D shapes into some kind of the latent codes, some kind of the middle layer here. Then what we can do is that we can basically use some kind of, for example, like some point net or any kind of the variant of the point net as the encoder, and then just make some kind of the simple the NLP to basically predict the set of the points as the output. So that was the very simple the idea that we can make some kind of the any kind of the encode the autoencoder of the point cloud, and also we can make some any kind of architecture that can take some any data the modality as the input. So we can basically make some kind of architecture like image to 3D, taking the image as the input and generating the point cloud as the output by just basically having the encoder for the images and the decoder for the point clouds. And that can be actually anything, like text to 3D. It's possible that we can make some kind of the text encoder and the point cloud decoder, basically training all the neural net with some kind of the pairs, given pairs of the input and the output, and with some kind of the reconstructed loss. So that was the very straightforward idea in terms of like making any kind of the encoding, the decoding, the architectures. So these are also some kind of the examples that we are just taking these images as the input and basically making some kind of the point cloud as the output for those kind of the cases. So it sounds like we can do any kind of 3D construction for now, right? But what are kind of limitations if we use this kind of the decoder for the point cloud? So if we make a neural net that can basically produce a point cloud as the output, what would be kind of the downside in this kind of the case? We also discussed some kind of the pros and the cons of the different representations with 3D data. But if we just recall all these things, what are kind of the downside of the limitations, the point cloud decoders? Yeah, requires lots of the points to get some all the fine details, no geometry information, taking lots of the memory. Yeah, so those are kind of some of the limitations, right? So obviously what we discussed last time is that obviously, for the point cloud, if we want to capture all the fine details in the geometry, then we might basically need to have some tones of the points to basically describing all the details. But the thing is that if we basically make a neural net that basically produces like, for example, like hundreds or thousands of the points as the output, then actually it will take lots of the time and also lots of the GPU memory in terms of like making some kind of the giant neural net. So that's basically very inefficient kind of architecture, making some kind of the point cloud as the output. And also one kind of the downside for this kind of architecture is that it's not possible to basically change the number of the points, which means that if we make a neural net architecture, for example, that produces like 1,000 or 2,000 points as the output, then once you train the neural net with the architecture produce, for example, like 2,000 points as the output, then you cannot basically produce like, for example, like 3,000, the more number of the points, because the network was basically trained to just produce the exact the 20 to 2,000 kind of the points. So we can also change the basically resolution of the output. So that's kind of the downside of this kind of the point cloud decoder. And also the downside that we also discussed last time is that typically for many kind of the application, we first need to basically convert all the point cloud into the other representation. That will basically involve the process that we are basically converting this point cloud into the implicit function and convert it back to the meshes or the other representations. So in terms of all the things, actually the point cloud decoder is very inefficient system that we cannot capture all the fine details, and also that also requires some kind of conversion to be used in the final the applications. Make sense? So the main topic that we are going to discuss for today is basically some of the architectures that can produce the implicit function as the output. So we also discussed the idea of the implicit representation, basically having a function that actually representing the shape as the kind of the some kind of output. And the topic that we are going to discuss for today is basically how we basically build a neural network that can generate not a point cloud as the output, but actually a implicit function as the output. So that's the basic idea. So if we go over with this simple idea, the first question that we're gonna have is that basically how we're gonna basically utilize the neural net as kind of the representation of the implicit function. So basically implicit function is basically a function, and we can also use the neural net as kind of that function that basically takes the 3D coordinates as the input, and then basically predicting either some kind of values for each of the point. Then we can basically consider basically having a neural net as kind of the implicit function that describes a basically shape. Does it make sense? So basically, given any kind of a single object, we can basically consider representing that shape using a neural network, which is basically taking any arbitrary point, the position of the coordinates of the point in the 2D or the 3D space, and basically outputting some kind of the values. So the value can be either some assigned distance or the occupancy value. So this will be basically the case that we are basically training our neural net. So in a way that the network becomes the implicit function described as 3D shape. Make sense? So that's basically a pretty simple idea. So then basically we can think about how we're gonna basically make such kind of the neural net by training. So we basically might need to basically provide some kind of training data to the neural net to train basically this kind of the network in a way that the network can basically precisely describe the shape that we have. So the first question is that we can consider the multiple types of the values as the output. So we can either consider basically predicting the signed distance as the output from the x, y, z coordinates, or we can basically consider some kind of occupancy function. So as we discussed last time, the signed distance was basically the idea that for each of the points in the either 2D or the 3D space, we are basically encoding the distance from the surface, the boundary of the shape to that point. But we are basically giving some kind of a sign as well. So if the point is inside, we can give the minus sign, or if the point is the outside, then we can give the plus sign, or we can flip the sign as well, right? So that is the basic idea for the signed distance function. Or the other way around might be is that we can basically simply basically provide some kind of the occupancy the values in terms of the if the points are basically inside we give the 1, or the points are the outside when we give the 0, or the other way around as well, right? And here also the quick question is that for each of the cases, if we have this kind of the either sign distance function or the occupancy function, then how we can also extract the boundary information. What will be basically the points that are basically on the boundary of the shape, or basically on the surface of the shape. For each of the case of the sign distance function and the occupancy function, what are the basically the points that are basically on the boundary of the surface of the shapes? If we just recall the things that we discussed last time. So the question was basically what would be, for each of the cases, what are the points that are basically on the surface of the shapes? Yeah, for the sign distance function, obviously the zero error set, basically the points where the sign distance function, the value becomes 0, are basically the points over the surface, right? So basically we can just need to find the points where the the value, the sign distance value becomes 0 for the points. Then the problem might be that for the occupancy function, what will be basically the points that are basically on the boundary, the surface of the shapes. Yeah, it depends on what we do. But typically what we can do is that since we assign 1 to the inside and 0 to the outside, if we think about like giving some kind of the continuous values for all the points, then we can consider that the points that are having the 0.5 as kind of the points on the surface, right? So, but that might not be the precise way, but it can be kind of the one way that we can do in terms of like extracting the surface information for these shapes. Right? So basically, we discussed the idea, basically, given this kind of the implicit function, how we can convert this into the voxels and also the meshes using the March cube, the ideas. Then also the question might be is that what will be basically the loss function that we can use for each of the cases? So let's think about these two cases. We are basically having a given the sign distance function and also the other, the occupancy function. Then how we can define the loss function for those kind of cases. So these will basically the cases that we are having the pairs, the input and the output. So for each of the points, we know the exact, the ground truth, the sign distance value or the occupancy value. And then how we can basically train the neural net so that the neural net becomes the implicit function, right? Yeah, I'm just asking very simple questions. Obviously, these are very simple things, but just checking whether you have some basic knowledge in the deep learning. So yeah, if you have some very basic knowledge when you deep learning, then obviously like something we can do is that for the sign this function, we can use some kind of the regression losses like L1 and the L2 losses. For the occupancy function, well, I mean, we can basically, this will be the case that we are having the 0 or the 1, the binary the values. Then instead of like using the regression the values, actually we can use some kind of the binary the cross entropy loss, which will be more effective in terms like learning with this kind of the binary the values. Right? Then let's think about some kind of real case. So we are having a kind of the 3D shape that can be represented into any form. Then we are basically wanting to basically learn, train a neural net that basically becomes the implicit function of the same shape. Then how we can basically provide some kind of training data into the neural net, right? So that's basically what we want to do. So given any kind of 3D shape, we want to train a neural net in a way that the neural net actually becomes a implicit function, right? For that, how we can basically provide the training data to the neural network. Uh, Another question. Yeah, obviously we will need to randomly sample the points. But for to all the randomly sample the points, we will also need to have the correct answer, the ground truth of the sign distance value or the occupancy value, right? So that basically means that given any kind of 3D shape, we will need to basically first convert the given shape into a implicit function first and provide all the values, the sign distance value or the occupancy, and then train the neural net, right? Makes sense. Then also, the question might be is that then this basically means that we already have the implicit function. Then what's the point of training the neural net? So that would be basically the question that we can ask. Like, if you want to train a neural net that becomes the implicit function of the point cloud or any kind of 3D shape, then you first need to have the implicit function to provide some kind of training data. Then what's the point? Why do we need to basically make the neural net of like, making the same implicit function, right? So compared to the other ideas that we discussed in terms of like making the implicit function, so we discussed some ideas, basically just finding the closest points to measure the some distance, or the moving least squares, or radius basis function, or the Poisson surface reconstruction, basically converting the point clouds into the implicit function, or actually there are some other direct way to basically convert the meshes into the implicit function, but whatever. So given this kind of some approaches that we can take in terms of making the implicit function, what would be the advantage if we train a neural net to make the neural net neural implicit function? Yeah, we can compress the data. We can get the implicit function with unknown objects. Yeah, we can get the values for the not in the samples. Well, actually, we are already having some implicit function where we can basically get some values for any points, right? So actually, we will get to that. Actually, one of the advantages, as you also some of you mentioned, that we can also achieve some generalization to the other 3D shapes. But even before that, actually, the good thing is that we can make some very compact representation of the implicit function. So in the case of like just converting the point cloud, also the meshes into the implicit function, would be is that we still need to have the point cloud or the mesh to compute all the values for any kind of arbitrary points for the implicit function. But by using a neural network, we can make some very compact the representation of the implicit function. Basically, by just having a simple DMLP that can basically encode all these kind of the sign distance or the occupancy information using some very compact the small DMLP. So in terms of like compressing the 3D the shape information, that can be really good. So that's kind of like one advantage. Also, one important thing is that if we want to basically have this kind of the implicit representation, as you can see, these are all the representation basically describing a volume, right? So for the cases that when we do not have any kind of the volume information, but some kind of some surface or something, or even when you have some kind of the volume like the shape, if we have some kind of small hole, so that basically makes some kind of difficulty basically describing, discriminating the inside and the outside region, then we cannot use this kind of some implicit representation because those are all the representation describing a volume. So that's all the very important things. So if you basically make some kind of this kind of decoder that basically generate all the 3D shapes as the volume, you first need to have some kind of the watertight shape. Basically, the watertight shape basically means that a shape that basically describes a volume that can basically decode the inside and the outside of the space. So basically, even when you have some kind of sphere-like the shape, if you have like small hole on the surface, so that we cannot basically decide whether the point is the inside or the outside, then we cannot use this kind of the architectures in terms like describing some volume information. So for any kind of the cases when you want to basically learn some kind of the implicit representation of these 3D shapes, you first need to have some kind of volume information, which means that you need to first have some kind of the watertight mesh or some watertight shape information that has some clear the boundaries of the inside and the outside region. So that's kind of one thing. Is it possible for the neural net to accurately represent the implicit function for any 3D shape? Yes. Yeah, so that the question for this is basically that the shape needs to be basically watertight. Any other questions? Okay, so moving on. So yeah, basically we need to have some kind of some conversion from the any representation then the other to the implicit function. And also the thing is that for training this kind of the neural net that becomes the implicit function, actually the sampling is quite important because basically we are much more interested in some kind of region in the 2D or the 3D space that are basically containing the surface, the boundary of the shapes, right? So basically what we can do in terms like improving the accuracy of the like describing all the details with 3D shape is that we can sample the points more near the surface. So basically one simple kind of some trick in terms of like training this kind of neural net is that we are sampling more points over the surface of the 3D shapes and perturbing all the points a little bit, like adding some kind of noise, as you can see in some kind of the some red points on the right-hand side here, in a way that we are basically having some more the points, doing some kind of important sampling, basically having some more points near the surface. But if you only take these samples near the surface, then you are basically also overfitting to these specific regions. Then we don't know what sort of the randomness we're gonna get for some kind of the rest of the area. So what we can do is that we can samples more near the surface. Basically, we can, for example, like take the 90% of the points near the surface and basically get some kind of information there while still basically taking some uniform sampling over the entire space for the 10% of the points. Then we can basically focus more on some kind of like getting some fine detailed information near the surface of the shapes. So this is basically the basic idea in terms of like training a neural net for a single object, right? And the question is that actually we want to make some kind of a 3D shape decoder that can basically produce not only a single shape, but also can some multiple shapes as well, right? Which means that we want to basically neural net that can basically decode basically the multiple 3D shapes. Then the idea is that the question is that how we can extend this kind of neural net in a way that they can basically decode some kind of multiple shapes. So one question is how do we know which point is on the surface? Well, I mean, in the case that when you have some given input 3D shape, so when, as I mentioned in the previous slides, this will be basically the case that we are basically somehow, representing the given 3D shape using kind of neural net. Then we will know, like, only the shape information, right? So basically, we can sample more over near the surface of the shape in this space, and still we can have some kind of uniform samples in the entire space. Is the bounding box annotated automatically? I mean, we can calculate the bounding box ourselves. Yeah, it's not the crucial part. I mean, we can basically decide some kind of region that we want to basically sample the points. And in that entire space, we can still take some kind of the 10% of the uniform samples while focusing more on the near the surface of the shapes. And also the question is that how are we going to extend this kind of neural net in a way that they can basically encode the multiple shapes, right? So actually there are some kind of the couple of the ideas for that. I mean, we'll be simple the ideas. Obviously, the other simple the idea is that we can basically combine this kind of decoder with the encoder. So basically, we are having some kind of the encoder here. They can take some either kind of the point cloud. If we want to make some kind of the autoencoder, then we can basically make some kind of 3D shape encoder, either taking point cloud, whatever kind of things as the input. And then we are basically getting some kind of the feature vector or some kind of the latent code for each of the input. And then we are feeding this kind of the extra the shape information as some additional the input to the neural net in a way that we can basically take some kind of the shape information here and also the XYZ coordinates as kind of the combined the input so that we can either predict the sign distance value or the occupancy function. So using this kind of very simple the architecture, basically having some kind of the multiple the linear layers in the MLP, we can simply basically make some kind of the neural network that can basically decode the multiple shapes. Right? Actually, the other way around is that we can actually consider having some kind of the sort of the meta function. So when you basically have this kind of the neural net, which is basically taking the XYZ coordinates and then basically predicting some kind of the either sign distance function or the occupancy values. We can basically have some kind of the another neural network, which is basically given any kind of input. This network is actually predicting the set of the parameters of this network. So it's basically predicting the parameters of the implicit function of a 3D shape. So given any kind of either the input image or input 3D shape, whatever kind of things, we are basically predicting a set of the parameters of the another neural network, which becomes the implicit function of the output the shapes. So that's basically the case that we are having some kind of the so-called the meta function that predicts the parameters of the other function. Okay, that makes sense. Yeah, so this is also some kind of well-known kind of the cases that we can see in multiple the applications that we are basically having a neural network to predict the parameters of the other neural network. What is the loss function for the meta function then? Well, I mean, we can use the reconstruction of the loss. So this will be also the case that we are having, for example, like image as the input, right? And some kind of the 3D shape as the output, right? So this will be input and 3D shape as the output, right? Oh, sorry. Oh my God. Here, image in and the 3D output, right? And for each of the 3D shapes, so we're gonna have some kind of the point, right? And some arbitrary the points that we sampled in the space. And for those kind of the points, we're gonna have some kind of either the occupancy value or some sign distance value, right? Then what we can do is that we are basically feeding this input image as the input here, and this network basically predicts the parameters of the other neural network here. That becomes the parameters here. And given the 3D coordinates, we are basically predicting either the sign distance value or the occupancy the value. And then we are basically training the entire network with the loss function here. So that's the simple idea. Can the number of the implicit function change? Number of the implicit function. Well, I mean, you mean the number of the 3D shapes? Yeah, obviously, we do not need to specify the number of the 3D shapes here. So as you also implemented the point cloud the autoencoder in the assignment 1, we can take any number of the pairs in this case. So it's matter of like how much the neural net has the capacity in terms of like, memorizing the input and the output the pairs. So we can train the whole network with the set of the input, the pairs of the input and the output. So the input and the output can be either images and the 3D or text to 3D, whatever 3D to 3D, whatever kind of things, and then training this network, basically having this kind of the network. Any questions on this? Yeah, very simple the idea. So actually, as I said, like the good thing of like having this kind of architecture, especially compared to the other some decoding architectures, is that as you can see here, the really good thing is that the network, the parameter size can be very small, as you can see in the previous slide. Here, I mean, even with this kind of like simple the NLP, the network, actually this simple the decoding architecture basically can decode some multiple shapes. So in terms of that, even with some very compact the architecture of the neural net, we can basically encode and decode some multiple 3D shapes. So that's really kind of the big advantage of this kind of the implicit representation. But as you can see, can you see the downside, the limitation of the implicit decoder? The problem is that it takes like tons of time for the inference. Any questions in this? Is there someone who is like sending message to me? I think I'm missing some of the messages. Yeah, let me move on. Let me know if you are sending some. What's the difference the models between the making another model that and just the use block correctly? I mean, these are two different ways of designing the decoders. Like actually, those two might make some kind of some small difference in terms of the performance at the end. But typically, whatever you use some kind of the previous idea or the second the first idea or the second idea, they are not making some big difference in the outputs. Just like different ways to basically make some decoder. What does the discretization mean in the table? Well, I mean, so these are, especially these two are basically the cases like having some decoder that basically decoding the voxels. basically predicting either the occupancy values or some kind of values for each of the voxels. So the output is always some values for each of the voxel with this resolution. So it's really kind of having some troubles in terms of that we cannot also change the resolution of the output. It's the same limitation of the point cloud decoder. So those two architectures are always basically predicting, generating the 3D shapes into this resolution. And the AtlasNet, let me briefly show the AtlasNet. AtlasNet is also the case that we are basically describing a 3D shape as kind of a set of the 2D patches. So now, as you can see in this example, basically describing the 3D shape as kind of some kind of the stitching of the all the 2D patches. So that is also kind of having some kind of the limitations in terms of the resolution. So basically, if you train the network with to produce the 25D patches, then we cannot basically increase the number of the patches. So having some kind of similar the resolution issues. But the good thing of the network that basically produce the implicit function is that we don't need to we don't have any kind of limitation restriction in terms of the resolution of the output. So in the test time, at the inference time, we can basically sample the points in the space as many as we want, and for all the points, we can basically get some kind of values. So we are not basically restricting the resolution of the output. So that's kind of the one big advantage of the implicit decoder. But as you can see, the downside is that these are also the cases that we are basically getting some kind of the point, the values, right? So basically at the inference time, we also need to sample lots of the points in the space and get some kind of either some values, right? So this will basically take lots of the time because for the other linear network, those will be the cases that are basically generating the 3D shape with the one single time kind of inference. But the implicit decoder will be the case that we are basically getting some of the values for each of the points, for the points that we sampled in the space. So basically the inference takes like way more time compared to the other linear network that directly basically generate all the values for the given the points or the voxels. So that's basically pros and the cons. So the implicit decoder can be some very compact, some kind of the neural net models that can produce the 3D shapes, but basically it will take some very longer time, way longer time, the test time to produce a single 3D object. So it's basically the pros and the cons of the implicit decoder. Does it make sense? So is that why the inference time is so slow for the? Yes, not only for the sampling, but also you need to get the values for each of the samples, right? So which means that you need to run the forward pass of the neural net multiple times for all the samples that you have. But the other architectures would be the case that they are basically predicting, generating the 3D shapes with a single time the inference, right? One time the forward pass. Does it make sense?
On the deep meta functionals paper, there was a parameter called scale that we were predicting with
I
this.
cannot hear you well. Can you speak?
Can you hear me?
I guess I need to increase the volume. Yeah, this is actually my maximum volume. Can you speak a little bit loudly?
Is it okay now?
Yeah.
Okay, so I had a question on the deep meta functionals paper. There was a parameter that we predicted with this auxiliary network called scale.
The parameter for what? Oh, sorry. The sound is not clear to me.
Is it better now or not?
Yeah, it's better.
Okay, so could you please elaborate on the scale parameter on the deep meta functionals? On this paper called Deep Meta Functionals. I think it was on your previous slide.
Here?
Yeah, there was a parameter called scale. This red box.
Scale?
Scale, yeah. It's one of the parameters that is predicted by network G.
I see.
F by network F.
Well, yeah, I don't know what the scale parameters there. Yeah.
Okay.
But basically,
So
this will be just some simple cases that you are having some simple NLP in the second network, and then you are predicting all the parameters for the second network.
yeah, I got this part, but like we're predicting weight, bias, and then there's this third one, which I don't have any idea what it could be.
Yeah, you can check these details. Yeah, I think this is not that important details.
Okay.
Yeah, so any other questions? So yeah, basically we are talking about that, the implicit decoder can be good in terms of like basically making some very compact the architectures for the decoding, but taking way longer time for the inference time. And also, yeah, as I said, also the good thing is that it does not basically restrict the resolution of the output. So basically, in the test time, we can basically produce 3D shapes with any randomly resolution as you want. But as you can see, for the cases that we are decoding the 3D voxels as the output, so if you basically train the neural net with some certain resolution, that you cannot change the resolution in the output. So that's also kind of the downside of this kind of the approach. And also, while it would be possible to represent a 3D shape as kind of a set of the patches, in this kind of the case, basically having some kind of the some stitching of all the 2D patches, for those kind of the cases, the kind of the problem is that it's also hard to basically produce 3D shapes with some kind of the arbitrary topology of the 3D shapes, having all the holes on the back side of the chairs. And also this might be same issue for the point cloud or the meshes as well, especially for the cases like predicting some generating the point cloud. If you have any kind of a set of points on the back side, in this kind of a case, it would be really hard to determine what the kind of some points that should be connected to each other, right? So basically not giving any kind of some topology information, but also the good thing of the implicit decoder is that they can be more flexible in terms of like producing any 3D shapes with any arbitrary topology, with also the capability of like describing all some geometric details. So as you can see, the implicit decoder can way better basically capture some kind of details in this kind of some complicated region of these 3D shapes. So those are kind of the advantages. And it can be actually used for any kind of some cases that we are having any arbitrary encoder and the decoder. So this will be the case that basically the encoder can be for anything, or it can be image or this text or some kind of even these 3D things. So this is example that we are taking some partial point cloud as input and producing the 3D shape as the implicit representation. For those kind of cases, basically we can make some kind of neural net that can basically complete any kind of given the partial 3D information. Right? And also one good thing of like having this kind of architecture is that if we basically encode all these 3D shape into some kind of the latent code, we can typically see some kind of the nice the properties of like having this kind of the smooth interpolation of these 3D shapes. So this is also what we are going to discuss in the later these slides. But typically the neural net is basically learning some kind of the smooth function, which means that if you make some kind of some changes, small changes in the input, then we're going to also see some kind of the small changes in the output as well. So it's not basically learning some kind of some function which is kind of like fluctuating. So what this basically means that practically in many kind of cases, if we make some kind of the encoding and the decoding the architectures, if you basically vary the given the latent code, so this is basically some of the examples that you're having this shape and this shape. For those two shapes, we are basically having the two latent codes that are basically given from the shape encoder. And if you basically linearly interpolate between these two latent codes, and then feeding this kind of the latent, the latent code into the implicit decoder, then you will also see this kind of the smooth kind of transition of the 3D shapes. Even with the cases that these two shapes are basically having some very different structure and the topology as well. So these are also kind of good properties that we are having some kind of the smooth interpolation. And if you compare this interpolation with like interpolating some the volume the occupancies, the voxel the occupancies, if you basically interpolate each of the voxel the occupancies, then you're gonna see this kind of results that the input shape basically disappears and the output shape basically appears over the interpolation. So this is not the kind of the ideal interpolation that we want to see. But basically, if we consider basically interpolating the latent codes that we have, then we're gonna see this kind of some very smooth interpolation between two shapes. So those are kind of some interesting properties. And basically, this kind of the implicit representation can be used not only for the 3D shapes, but for the any representation. So basically, the implicit neural representation now is quite famous for all the the modalities like the images and the videos and the audio as well. And this is kind of like one of the examples that we are also learning the super resolution in terms of the using some kind of the implicit representation. So what we can also do is that given any kind of the low resolution the image and the higher resolution image for those kind of the pairs, we can basically take some kind of this low resolution image as the input and basically make some kind of the neural network that predicts the high resolution image as the implicit representation. So for any kind of the point in the 2D space, we are basically predicting the color information, right? So in this way, we can basically make some kind of neural net that can do also basically doing some kind of super resolution, increasing the resolution of the input image. And the good thing of like having this kind of architecture is that we can basically choose any arbitrary resolution for the output of the image. So that's kind of the advantage of like having the implicit representation. Makes sense. So yeah, in summary, basically the good thing like having the implicit decoder is that the network can be basically very compact, while still basically encoding and decoding all the fine detailed information. And we can also basically change the resolution of the output. And also this architecture can be very flexible in terms of all the arbitrary topology of the 3D shapes. But the downside is that it basically takes a very long time to basically generate the final outputs. Basically, we need to basically infer the values for each of the points. So that's kind of the pros and the cons of the implicit decoder. Any questions? So if we move on, actually, so this is basically very general the idea for some implicit decoder. Then let's think about the case that we are having the image as the input, specifically. Specifically, let's say the input is the image and the output is the 3D. So that's basically what we are going to discuss for some of the next lectures. For those kind of the cases that we are taking the image as the input and 3D as the output. Now what we can see is that we can make some basically very simple architecture that is basically taking the image as the input into some kind of the image encoder. Taking image as the input, and then 3D as the output, right? And for this decoder, we can use the implicit decoder, right? It will be doable, right? Then what will be kind of the downside of this? To scale the network model, how do we scale implicit decoder? Have to train from scratch? You mean how we train the decoder with some, a set of these 3D shapes? You couldn't get the point. Basically, the question was like, how do we scale the implicit decoder? Have to train from scratch? Make it deeper, for example. Well, I mean, it's just a matter of the choice of the architecture. If you basically make an MLP architecture for the decoder, you can basically stack more the layers. Yeah, so we didn't discuss any ideas about in terms of how we design the architecture of the neural net. But basically, typically, as we have seen in the previous slide, we can make some kind of simple the MLP the architecture with some kind of linear D layers. And it's a matter of like how many layers you stack in the network, right? Makes sense. And let's think about this simple case that we are having some, a simple the MLP here as the decoder and some kind of image encoder here. So basically mapping the image into some kind of the latent code here, and then basically decoding this latent code into using some kind of the implicit decoder, right? Yeah, obviously we train the encoder decoder jointly. This is exactly the same as the PointNet-based the autoencoder that you implemented in assignment 1. But the only thing is that we are just switching the decoding part. Okay. This is exactly the same with the autoencoder that you implemented, but we are just discussing the idea in terms of how we can switch this decoder into the implicit decoder, right? And here the question is that would it be kind of the best architecture in terms of basically mapping the image to 3D, especially for the case that we are having the image as the input, not text or audio or something else. In the case that we are having the image as the input, if you basically took the either computer graphics or the computer vision the courses, basically the 2D is basically the output of the rendering of the 3D shapes, right? So if you have any 3D shape in the 3D space, then the image that we get would be basically the output of the like rendering, basically projecting the 3D shape into some 2D plane, right? By the way, how many people here took the computer graphics course before? Thumb up if you took the computer graphics course. No one took the computer graphics course before? Yes, no? Well, yeah. What if you did not take the computer graphics course? I mean, basically, you don't need to have all the knowledge about the computer graphics, but basically, like, all the things that we are basically learning in the computer graphics course is basically how we render the 3D shape into the 2D plane, right? With some kind of the matrix the multiplication. But basically, the idea for that is that we are basically projecting the 3D shape into the the 2D plane, right? So which means that we will be able to have some kind of some corresponding information between the 3D and the 2D. So what we can see is that each of the points in the 3D space will be able to basically project it to the 2D point, which means that each of the pixel in the input will basically contain the information of the points that are basically the intersection between the ray that we are shooting from the 2D plane into the 3D space, right? So here the basic idea is that instead of like just encoding the entire image into a single latent code and decode this back to the 3D shapes, what we can do is that we can basically actually encode the information of each of the pixel here with some kind of some fully convoluted neural net that is basically combining also the local and the global information of the input image. So basically what we are going to do is that for each of the pixel, we are getting some kind of the pixel feature, which is basically obtained by basically some kind of the either convolutional neural net, or you can use some kind of transformer, right? So basically combining all the global and the local information for this specific point, and using this specific point to basically predict the information of the points that are on this specific ray. Because we know that these points in the 3D space are basically the points that are basically corresponding to this specific pixel. So we are fully utilizing this kind of some spatial information, like what are the 3D points that will basically come from the 2D pixel in the image that we have. So that's basically the things that we can make some kind of difference in terms of the, instead of like, encoding the entire image into a single latent code and decoding this back to the 3D, we are fully utilizing the correspondence between the 3D points here in the 3D shapes with the 2D pixel in the input image in a way that when it basically predicts some kind of the side distance or some occupancy values for each of the 3D points, we are basically predicting this information not just based on the global information of the input image, but based on the pixel information, which is coming from as kind of the projection of those 3D points into the 2D plane, right? What's the difference with the MVCNN? Well, MVCNN was the case that we are just like encoding the multi-view images. Here, the question is that given some images, how are we going to basically decode 3D shapes by utilizing this kind of the 2D to 3D, the correspondence information? MVCNN was about the encoding. So this is about decoding. Make sense? So that's the basic idea of this kind of this kind of like the cases like learning the implicit function from the images. So here basically the setup is that we are having either a single or some multi-view images as the input, and the output is basically not some kind of some classification score or something, but basically we are basically wanting to basically predict a implicit function that describes a 3D shape. And here basically we are also having all the camera pose information, like where basically we capture the images and how the 3D shape can be basically projected to each of the plane, the view plane, right? So given this kind of information, how are we going to fully utilize this kind of the specialty alignment of the 3D and the 2D is basically the idea in this kind of the cases. So basically, these are some of the examples that we are taking these like images as the input and just generating these 3D shapes as the output, right? So if we move on to, So for basically here the basic idea is that now we are basically fully utilizing some convolution neural net in terms of like generating the features for each of the pixel. Then for all the points along this ray in this 3D space. So let's say this X is the pixel that we are interested in. Then for all the pixels along this ray, we are taking the XYZ coordinates in the 3D space, and also the feature of this specific 2D pixel in terms of predicting either the sign distance function or the occupancy values. Where in this way, we can predict not only some geometry information, but also some appearance information, like the color information as well. Then in terms of that, we can basically get all the geometry information and also the color information to get some this kind of the colored this 3D shape as the output, which typically gives some way better the outputs than just having the simple encoding decoding architectures, because we are utilizing the alignment information between the 2D and the 3D. So we are to predict the values for each of the 3D points. We are not using the entirely just like single the global latent code of the input image, but we are basically using some information for this specific pixel, which is the projection of the 3D point into this specific 2D plane. Does it make sense? Then here the question that we can actually ask might be is that, then what's the difference with the depth prediction? Also, there are lots of kind of the neural network that takes this input image, the color image as the input and predicting the depths, right? So we can actually consider this as kind of another kind of way to basically construct some 3D information, taking the color image as the input and predicting the depth image as the output. There are already such kind of the neural network predicting, learning the depth information. And what's the difference with this depth prediction in this case? Well, I mean, this is still also the case that we are learning some view kind of dependent information, right? So we are basically projecting these 3D things into the specific view that we have and getting some kind of information. So actually the question is that what's the difference just between predicting the depths and predicting implicit function in this case? Obviously, we are not only getting the geometry information, but also some color information as well. That can be one difference. Yeah, so basically the major difference is that for the depth prediction, we are only predicting the geometry information of some visible area from this specific view. So basically depth means that we are getting the distance to the first intersection points, right? So if you shoot a ray to the 3D object, you're gonna have the first intersection point, right? So distance to this like the first intersection point is the depth information. So predicting depth means that we are only getting information of the visible area from that specific view. But obviously we want to also get the information for the occluded area for the backside of the 3D objects. So basically beyond the points of the first intersection. So depth prediction is basically not learning this kind of the full geometry, but only the geometry of the visible area from that specific view. But what we can do in this specific kind of architecture is that we can get
all the information even in the occluded area as well, in terms of that when you shoot the ray along this ray for all the points in the 3D space, you can get some geometry information, the sign distance for the occupancy, in a way that when you have some kind of the object here and the other objects here as well, you can see that, yeah, these points are basically outside, and these points are inside, and these points are also outside as well, and these points are inside as well. Basically, so getting some kind of all the full 3D shape information, including the occluded region as well. So that's basically the major difference between the depth prediction and the 3D, the implicit, the function prediction in this case. Makes sense? And obviously, even when you also have some multiple images as well, we can also utilize the same architecture in terms of like doing some pooling. So now when you have some multiple views that are basically having some two different pixels, which rays are also intersecting at this specific point, then we can basically take the features from the different pixels and take some kind of the pooling the outputs. We can use the average pooling or whatever the poolings in terms of like aggregating the pixel information, and do the same thing in terms of predicting sign distance or the occupancy. And let me show some of the outputs here. So as you can see, these are some of the outputs, basically taking the images on the left-hand side as the input and predicting some of the 3D shapes. And let me show some video as well.
Although our approach is trained on a synthetic dataset, it's in this.
So it's taking some time. I don't know why this video is not playing. But yeah, I will send you the link of this video, but you can basically check out the quality of this video here. So actually it's quite good in terms of, as you can see, even this like the still image, you can see that the output 3D shape is capturing some details in the input 3D shape. But obviously, as you can see here, it's not capturing all the fine details, but still basically getting some kind of the good outputs. So yeah, let me just move on. Yeah, you can check out the link in the Zoom chat. Yeah. Okay, so let me move on. So actually the most important part is here. So here the thing is that, well, I mean, so given the implicit decoder, actually we can basically produce some kind of these, some of the 3D shape the outputs. And actually also this implicit decoder, this idea can be applied to the any data modalities, also for generating some of the images or the shapes, and also the audio video as well. For those kind of the cases, these are some of the outputs that we can get in terms of getting some kind of generating either images, shapes, and the audio. And the thing is that, like compared to some other representation, like having the point cloud or something, this is kind of the good kind of the idea in terms of like that we can capture some details, but still it is basically failing to capturing some very high frequency, some fine details. As you can see, for some very fine details, you can see in the image here, actually the output image looks a little bit like blurry, right? And also the outputs of the image is basically not capturing some kind of the fine details, some high frequency details quite well. And here the question is that what's the problem with the architecture that we have? How can it basically make a neural net that can basically achieve this level of the reconstructed quality? So basically here the idea is that by just making some very small changes in the given the neural net architectures, actually we can improve the final the generation the quality a lot like this, basically making all the capturing all the kind of the details as you can see here, while if you just use some simple the typical the MLP, then you're gonna get this level of the quality. So here the question is that why we are getting this kind of the low quality in terms of missing some of the high frequency details, and how we can basically improve the architectures in terms of like getting some all the details. And this is another example that we are also reconstructing all the 3D things and also images in the 3D
reconstructing some dragon or some kind of some medical images for those kind of cases. Depending on how we basically design the architecture of the neural net of the implicit decoder, we can get very different qualities of the outputs. So here the question is that why we are missing some of the high frequency details in the output function. So in terms of that, when you see the output as kind of the signal, basically having some kind of some functions that are basically we are having some having some 3D or the 2D the outputs. What we can see is that typically for those kind of the cases that we are having some very defined details, having some sort of the high frequency details, those will be the cases that basically if you so basically implicit function is a function, right? So if you take the derivatives of this kind of function, for the cases that we are having some fine details, the first, second, and higher order derivatives will not be zero, right? Also, the functions, the derivatives of the functions that we are generating will be some kind of the non-constant functions. But the thing is that let's think about the MLP network with the typical ReLU activation. So when you basically make some kind of the neural network with the linear layers, the way that we are basically adding some kind of the non-linearity would be basically adding the activation function, right? So without the activation function, we are just like stacking some linear layers, right? Which means that the whole function that we are going to learn would be basically a linear function, while the function that we want to basically learn is a highly non-linear, basically fluctuating some functions like this, right? So the thing is that the only way that we are adding some kind of the non-linearity is basically adding the activation function. But the typical activation function that we are using is basically the ReLU function, right? And what we know about the ReLU function, if you have this background, is that basically this will be the case that we are making the function like this. So the value becomes the function becomes linear when the input is the positive, and also it becomes a zero in the negative regions, right? So what we can see is that actually the activation function that we are using is also piecewise linear function, right? Actually, that's kind of the way that we are adding some kind of the non-linearity. So the thing is that the activation function that we are using is basically piecewise linear function, which means that if we take the derivatives of this, like the entire function, still the first derivative will be some kind of a constant, and the second and the higher order derivatives will be zero function everywhere in the input space. While the input function that we want to predict is the function which the second or the higher order derivatives is not zero. It's basically a very complicated function. So which means that by just taking some linear layers with the ReLU activation, it's impossible to basically produce the function that we want to achieve, because the function that we want to get is basically a function which derivatives, the second and the higher order derivatives, are basically not zero. And that's kind of almost the same for the other deactivation as well. If we see how the other deactivation, the functions are introduced, those are kind of like some functions that are quite similar with the ReLU, which is not kind of like this was linear, but they're basically second and the higher order derivatives also becomes almost zero for most of the places, which means that using this kind of deactivation function in the linear layers, it's really almost like impossible to basically reconstruct the function, basically having some kind of the high frequency details, which basically second and the higher order derivatives are basically not zero at all for most of the places. So here the simple idea is that we are basically switching the activation function into the much more the complicated function, I mean in terms of the shape, not the formulation, like this. Basically, we are taking some kind of the sinusoidal function as our the activation function. Then the good thing is that we know that for this kind of like sine or the cosine function, the derivatives with any order cannot be zero, right? So which means that when you use this kind of like sinusoidal function as the activation function, then we can still now we can make some kind of the reconstruct some kind of implicit function, which basically second or the higher order derivatives becomes non-zero functions. So this is kind of like some examples when we use the sinusoidal function as the activation in the MLP layer. The last column. And the other the columns are the cases like using the other the activation, the functions in the neural net architectures. So first of all, you can see that the case that we're using the sinusoidal function as the activation function converges way faster. So let me start again. So if you see from the very beginning, from the first few iteration, the cases that we are using the sinusoidal function as the activation converges way faster, while the other cases using the other activation the functions are making some kind of blurry the outputs, very blurry the outputs, and also takes much longer time for the convergence. And also the good thing is that even from the first few iterations, we are not only reconstructing the given the function, impulse function, but also basically quite precisely reconstructing its derivative as well. So this is the case that we are only basically trained the neural net with the ground truth of the pixel values, basically the impulse function itself, not its the derivatives. But even in the case that when we did not provide any information about the derivatives of the function, we are getting some quite good the accuracy of the first derivative as well, and also the second derivative as well. So if you compare the first and the second derivatives with the first and the second derivatives of the input here, you can see that actually these two are quite almost the same, even if the first few iterations. Even in the case that when we did not provide any information from the gradients, basically the derivatives of the input function. So that's kind of a good thing. So which means that like choosing some right the activation function is really important in terms of getting some very high accuracy in the final the outputs. Make sense? Is the finding only valid for the impulse function? Is so why does it not scale for other tasks? Actually, yeah, that's what we are going to discuss for the next few slides. This finding is valid for the many other cases, but this is especially effective in terms like learning the impulse function, especially when the function that we want to learn is kind of some complicated function. But this actually idea can be used for any other cases that we want to learn some kind of the complicated function where the derivatives become not zero. So actually what we are going to discuss in the later slides is that actually this idea is kind of like related to the positional encoding that people are using for the transformer. So those are all the kind of the concurrent ideas that basically came up almost at the same time. But basically, as you can see that the positional encoding is used in the many other places. This is quite, generally the idea that can be applied to the many other tasks. But this idea is especially very important in terms of like learning some impulse function using the neural net. So if I show one more slide here. So even this is the case that we are now training the neural net by just providing only the gradient information. So now the only information that we are providing is basically the first derivative of the input function. And then we are predicting a function in a way that the first derivative of the output function becomes the same with the given the information of the first derivative of the input function. So even in this case, so what this means is that now we are only providing information of the second row. The ground truth is given for the second row, basically the first derivative. And what we can see is that even in the case, we can see that in the first few iterations, the case that we are having the sinusoidal activation function can almost perfectly, reconstruct the input function, even without providing the input function information directly, while the other activation cannot basically predict the output the function at all, because even they cannot basically predict the first derivatives precisely. So that's kind of also the case. And as you can see, this will be the case that we also have seen this kind of case in the previous lectures, right? The Poisson equation was the case that we are reconstructing the input function only from the derivatives. And this is basically the case that we are solving some kind of the Poisson equation using the neural net. So the question is that basically when you provide only the first derivative information to the neural net, whether the neural net will be able to basically find the solution of the basically the function, which derivatives becomes the same with the derivatives that we are providing. For those kind of cases, if you basically use the other deactivation, the function, it will be really difficult to find the solution. While when you basically use the sinusoidal the function as the activation the function, because it can basically learn all these kind of the high frequency details very quickly, we can also get some kind of the results, so like reconstructing the full input the function. So that's very interesting the results. And also the same idea, like reconstructing 3D shape as well. So
Right.
display this.
A single fully connected siren with 5 layers and 1024 hidden units may also faithfully represent a full-scale room, while a ReLU network fails to faithfully reconstruct the room, as illustrated by the inability to fit the curtains, the bowl on the table, or the feet of the sofas.
Yeah, so as you can see here, compared to the case that you're using the ReLU function as the activation, when you use the the siren, basically the sinusoidal the function as the activation, you can get way better quality in terms of getting all the fine details of the geometry. So that's the basic idea. So since we are running out of time, let's continue discuss this the activation the function in the next time, and after that we are going to move on to the neural rendering. Any other questions? Any questions to this lecture? Okay, let's stop here and let's continue on Wednesday. Thank you.